Okay, let's have a little bit of fun using the inverse square law. How bright would the moon be if you were standing on it? So I'm going to light up a piece of paper with the moon and take a look. So I couldn't find any paper, so I wrote my name on a piece of paper towel. And as you can see, with the moonlight, I can read my name perfectly fine. Now let's compare it to a regular light. Okay, here's a big building. Let's make it dark in here. Okay, I mounted a 60-watt light bulb to the wall. I use a 60 watter because everybody knows how bright a 60-watt light bulb is. And about 50 feet away, here's what the sheet of paper looks like. Okay, so the moon one is on the right and the regular light bulb is on the left. So you can see they're pretty similar. Now, don't get your panties in a bunch. I know you should be using a light meter and all that stuff. Wait till the end. It's not going to matter. Okay, so the moon is 1,256,640,000 feet from the Earth. Now, a 60-watt light bulb at 50 feet is roughly the same brightness as a full moon. You can read the paper about the same. So we're going to use the inverse square law. Okay, so we're going to take 50 times 25 million, and that puts us at 1,250,000,000, which is pretty close. Now we're going to square this number. So 25 million squared is 625 trillion. So now we got to take 625 trillion and times it by 60 watts, and we get 3.7 gajillion, bazillion, zillion plus 16. This number is so big that I think my calculator exploded. So you can see there's a huge problem here, right? So let's just call it 1-to-1, okay? Let's just go 1-to-1 ratio. Instead of like 1 to 5 bazillion, gajillion, bazillion, bazillion, jillion, we're just going to go 1-to-1. And let's see what it looks like. Okay, here's our little moon landing guy. Okay, let's land him on the moon at 1-to-1, 60 watts. Does that look normal to you? Is that what the moon landing looked like? Come on.
The inverse square law of light is simply not applicable to anything in space. Flat earthers discovered that the moonlight on the moon's surface would be intensely blinding based on the official numbers of the heliocentric model. The inverse square law of light works like this. If you place a 100 lumen bulb in a floodlight that shines on only 1 square meter of surface, that surface will be lit at 100 lux. However, if you back the floodlight away to shine on 4 square meters, the surface is now lit with 25 lux. The intensity of light is inversely proportional to the square of the distance. This means that as the distance from a light source increases, the intensity of light is equal to a value multiplied by 1/d squared. The full moon, which is supposed to be reflecting sunlight, has an illuminance up to 1 lux on the Earth's surface. Look at this diagram and imagine that the light source is the moon and you're standing on the Earth's surface there on the bottom right corner. Each step higher you go, the moonlight gets more intense. So, based on the official distance to the moon and a 1 lux strength of moonlight on the Earth's surface, the Apollo astronauts would have experienced many thousands of times more illuminance on the moon's surface than direct sunlight on Earth. Every photo of the moon's surface would have been impossible and washed out.